Hi, welcome to your Mac 200 Statics online classes. My name is Dr. Diaz, and in this first part of Chapter 1, you'll be introduced to some of the general and basic principles of statics. This is one of the most fundamental and fascinating branches of engineering, and I hope that you all enjoy this journey through the statics world. Let me start by quickly highlighting the objectives of the chapter. We'll start with some definitions and then describe the basic quantities of the most important idealizations of mechanics. Next, a statement of Newton's laws of motion will be given. Then, we'll briefly review the principles for applying the international and the US customary system of units. And finally, we'll examine the standard procedures for performing numerical calculations and present a general guide for solving problems. Let's get it started by providing a clear definition of what mechanics is. You may already be familiar with these concepts from the physics courses you took in the past, but it's a good opportunity to get your minds refreshed right now. For all purposes here, mechanics is a branch of the physical sciences that is concerned with the state of rest or motion of bodies that are subjected to the action of forces. And that's a formal definition of mechanics that you can find in most of the dictionaries. In general, this subject can be divided into three branches: rigid body mechanics, deformable body mechanics, and fluid mechanics. In this course, we'll focus mostly on the rigid body mechanics, which is further divided in dynamics and statics. Whereas dynamics deals with the accelerated motion of bodies, statics studies the equilibrium state of bodies. In other words, those that are either at rest or move with constant velocity. Statics is an essential subject for the design and analysis of several types of structural members we find in engineering applications, like bridges, buildings, and vehicle structural components. We begin our study of mechanics by defining the four basic quantities used in this area, which is a quite intuitive task to us. The first one is the length, which is used to locate the position of a point in the space and therefore describe the dimensions of a physical system. The second one is the time. Although most of the principles of statics are time independent, this quantity plays an important role in the study of dynamics. The third one is the mass, which is a measure of the quantity of matter that is used to compare the action of one body to another. In statics, the interaction of the mass of a body with the gravitational field of the Earth is very important to define the weight of that body. And the fourth one is the force. In general, force is considered as a push or pull effect exerted by one body to another. Forces are generated when a body is in direct contact with another body, or when a body is subjected to a force field, such as the gravitational, electrical, and magnetic fields. In any case, forces are vectorial quantities, characterized by its magnitude, direction, and point of application. Now, let's take some time to review some of the most important idealizations we are going to use in the analysis of statics problems. It's important to mention first that the main goal of idealizations is to simplify the mathematical model. Yes, the mathematical equations resulted from real statics problems can be quite complicated, and the idea here is to simplify them as much as we can by applying idealizations. The first one is the particle idealization. In this one, we assume that the body behaves like a particle, in which we account only for its mass, neglecting its size. For example, when studying the orbital motion of the Earth around the Sun, The size of the Earth is insignificant compared to the size of its orbit, and then the Earth can be modeled as a particle. This brings a huge simplification to the problem, since we don't need to worry about the geometry of the body under analysis. The next idealization is the rigid body model, which assumes that the body is a combination of a large number of particles, in which all the particles remain at a fixed distance from each other, both before and after applying the load. This is the same of assuming that the body shape will never change, whatever the load applied. This is a very useful assumption, since the amount of deformation occurring in most of the real structures is relatively small, making the calculations much easier to do. The last idealization regards the concentrated force assumption. This represents the effect of a loading which is assumed to act at a single point on the body. Let's consider, for example, the contact force between a railroad wheel and the ground. In this case, the area of the rail over which the load is being applied is much smaller compared to the overall size of the rail, and then we consider a concentrated force on the rail. Additionally, since the railroad wheel is made of steel, which does not deform very easily under load, we can also assume that it behaves like a rigid body. Now, we are ready to review the main equations used to model statics problems. All the field of mechanics, including statics, is formulated on the basis of Newton's three laws of motion. These laws were first formulated by Sir Isaac Newton over 300 years ago, and are still valid today for most engineering applications. These laws are applied to the motion of a particle as measured from a non-accelerating or inertial reference frame. Let's briefly review their statements. The first law states that a particle at rest or moving in a straight line with constant velocity tends to remain at this state if the particle is not subjected to an unbalanced force. This is the law that assures the equilibrium state of a system when subjected to perfectly balanced forces, and we're going to use this one a lot when solving statics problems. The second law states that a particle with mass m, acted upon by an unbalanced force F, experiences an acceleration a that is in the same direction and has a magnitude directly proportional to the force. This law gives us the famous Newton's equation of motion, F equal m times a, or force is equal to mass times acceleration. And the third law states that the mutual force of action and reaction between two particles are equal, opposite, and collinear. That's the so-called law of action and reaction, and we'll also be referring to this law a lot in our calculations. As a consequence of his three laws of motion, Newton postulated a law governing the gravitational attraction between any two particles. This is mathematically expressed through the following equation, where F is the force of gravitation between the two particles, G is the universal constant of gravitation, R is the distance between the two particles, and m1 and m2 are the masses of the two particles. A special case is if the particle is located at or near the surface of the Earth, like an astronaut orbiting the Earth. Then the force acting in the particle is its weight, given by the following expression, where W is the weight of the particle, m is the mass of the particle, and g is the acceleration due to the gravitational field of the Earth. Observe that in order to a body generate a sizable gravitational force to another, its mass must be much bigger than the mass of the other body, like in the case of the Earth and the astronaut. After introducing the basic quantities, it's time now to present the units of measurements we are going to use to quantify those basic quantities. This table shows the units used to express the four basic quantities in the International System of Units, or simply SI, or in the United States Customary System, also known as FPS or Foot-Pound-Second System. It's important to observe that each system has its own unit derived from the other three basic units. In the International System, the force, measured in newtons, is the force required to give 1 kilogram of mass an acceleration of 1 meter per square second. Likewise, the mass, measured in slug, is the derived unit in the US customary system and is defined as the amount of matter accelerated at 1 foot per square second when acted upon by a force of 1 pound. Both the international and the US customary systems are used quite often for engineering calculations. For this reason, it would be helpful to establish a set of direct conversion factors between them. This table provides the conversion factors from the FPS to the SI units. Obviously, if you want to convert from the SI to the FPS, you have to divide 1 by the values listed in this table to get the new conversion factors. Also, in the FPS system, it's good to have in mind some quick conversion factors, like the ones from foot to inches, from miles to foot, from kilopounds to pounds, and from tons to pounds. Today we have powerful calculators to do this job for us, but having some of these conversion factors in the back of our minds really helps to do quick back-of-the-envelope calculations. And that's the end of this first part of Chapter 1. Thanks for watching, and I'll see you in the next video.